Welcome everyone to the Rancho Mirage Library and Observatory. My name is Eric McLaughlin. We're going to be getting started here shortly. If you're watching this live, feel free to start putting some questions in the chat. If you are watching this as a playback, again, we just have this time frame to let people get into the chat, so we have some people here right when we get started. So while we are waiting to get started, enjoy these live views of the sun and a little bit of music. Welcome everyone to the Rancho Mirage Library and Observatory. My name is Eric McLaughlin, and I'm joined today on camera by Lauren Zuckerberg, our observatory program coordinator. And we're here to answer and address all sorts of questions you guys have. We're going to jump into it, but a few things right off the bat. We are going to be using a lot of software that allows us to travel around and look at things in a lot of different ways. I am by no means a perfect intergalactic pilot, so there might be some little happenstance along the way, so that might drive a little bit of flashing lights. So please keep that in mind as you are watching. I should not ignore the fact that we are also joined here by Ron Treat, one of our observatory docents and one of our observatory and library advisory commission members. He'll be in the chat there for you, helping address the questions that come up and help feed us questions as well. So, with all that said, I think we're about ready to jump right in, and we actually threw one on the bottom here already. The questions we're going to start with are ones that our staff actually gave us, so that way we can start to get a little bit of thoughts in your mind on what you might want to ask. And why not start with one that is so common, that comes up all the time. We honestly get a little tired of answering it, so let's just get it out of the way right at the beginning, and that is, what's going on with Pluto? Is it classified as a planet? And the answer to that is involved and requires thinking about a full set of things. So first and foremost, it is currently classified as a dwarf planet. Nothing's changed about the planet, or the dwarf planet, the planetoid, whatever you want to address it as. It is officially classified as a dwarf planet. And to address how that happened, we're going to go on and include along the way another question. But before we get there, let's start looking at how we'll be answering these questions. And we're going to start by showing you that we are using a wonderful program called SpaceEngine. This is the view from the observatory as shown in SpaceEngine. And when you're looking at that, you might think that doesn't look so much like the valley I know. There's nothing here. Well, it's a simulation of the entire universe. It's going to be missing some details like, human settlement. But in any case, you can actually see over there is Mount San Jacinto, and over there is San Gorgonio. And in any case, let's go ahead and leave the planet behind and start exploring. So the first way we will actually start addressing how Pluto got reclassified, we need to actually look at some historical context. And I realized I left something on here I didn't mean to. Let me just switch off that there. We don't need a grid over the Earth. Get that out of here. Okay. Now,
and I'll jump in for a second here.
Yeah.
Good afternoon, everybody. Thanks for coming. And I just want to point out that this question came from one of our reference librarians, Craig.
Yes. Thank
you, Craig.
Yeah. Again, jumped right into it. Lauren is going to be keeping me in check, so that way I don't just monologue the entire time, especially. Now, so
do my best.
Yeah. So if you could go ahead and get the second question in there as well.
Sure.
Let's see. That would be
this one, like the second half.
That one.
Oh, gotcha.
Yeah. So in order to answer the first question here, we are going to be addressing another object, and that object is the largest object in the asteroid belt, and that is the dwarf planet Ceres. And so let's go ahead and make our way there.
And this question came from our clerk, Jay Fabian Penentel. So thank you, Jay.
Yeah. And so why are we going to the asteroid belt if we want to talk about Pluto? Well, in 1800, there was an object found in the area between Mars and Jupiter. That object was actually somewhat predicted. When we were looking out at the planets and getting all their locations figured out and everything, we noticed that there was an interesting gap between Mars and Jupiter, and someone predicted there should be a good-sized planet there. Why haven't we found it? So people went looking for it, and what was found in 1800 was Ceres. this object here. It was found there, and then over the next 50 years, a number of other objects were found in the vicinity of the orbit of Ceres. And once enough of them were found, it was realized that this should be classified differently. And as a result, what happened over those 50 years was the discovery of the asteroid belt. The term asteroid was then coined, and Ceres became the largest asteroid known. It is a fascinating object. It is nearly spherical, and it has a lot of interesting activity on it. You might notice those nice bright spots there in the center there. Those are believed to be cryovolcanoes, though there is a bit of research still yet to be done. And if I'm remembering correctly, it was the Dawn mission that made its way here. So again, over a course of 50 years, this object was a planet, but it was reclassified as an asteroid, and then with Pluto's redesignation, because this one is nice and round, it was reclassified as a dwarf planet again. But the asteroid moniker still kind of sticks with this one. So what else then? Well, let's actually go and talk directly about Pluto. Pluto was discovered quite a bit later. Let's see. My brain is blanking on that discovery date. Let's fly off that way.
We are on it.
Yeah. Thankfully, I'm not working alone, and we can remind ourselves of that. So,
Yep, 1930.
It was 1930.
Thank
okay.
you, Ron.
Yeah, so 1930 was when Clyde Tombaugh found it at the Percival Lowell Observatory, and one of the reasons it got designated Pluto was that the symbol that they used for Pluto is a combination of the letters P and L, and as such, it is a nice little way of not naming the planet directly after Percival Lowell, who, again, built the observatory it was found at, but it was a way of subtly noting where it was discovered. Now, again, this object was found in that time frame. It was classified as a planet, and it does have a rather sizable moon. It actually has a number of moons, but its largest moon is Charon, which often is pronounced Sharon because of the person who discovered it wanted to name it after his wife, Sharon, but they couldn't do that because that's not the way naming conventions work. And as a result, sneakily just changed the pronunciation of the ferrymen across the river Styx. And so the mythological pronunciation is correct as Charon. The romanticized fun way of pronouncing it is Sharon. So I'll leave that up to those who reference it. But again, prior to 1930, out beyond the orbit of Neptune was predicted a interesting new planet, Planet X. There should be a sizable planet out there. And when people started looking out there for it, Pluto was found. Now, I should note back with Ceres, finding Ceres was not the planet they were looking for. They were looking for a much larger object than Ceres. Likewise, Planet X was supposed to be much larger than what was found with Pluto. And so Planet X was not actually found. Instead, this object was. Then over the course of the next 70 or so years, a whole bunch of other objects were starting to be found out there, the trans-Neptunian objects. And so when we are looking out at that distance and finding a whole bunch of other things, it is worth understanding that, yeah, it's not just one specific type of object out there. This is the flagship for an entire new category of objects, the objects in the Kuiper Belt. And as it is a very specific size and has very specific dynamics going on with it, again, being fairly spherical, it made sense not to say, oh yeah, let's just lump it in with the asteroids or lump it in with comets. It's unique, and we need to actually figure out a good way of classifying it. And that's what led to that classification, dwarf planet, being made specifically because of objects like Pluto. Now, what makes a dwarf planet different than a planet? Well, the specific definition is very similar, except that a planet is massive enough to clear out its orbit of all similarly sized objects. Pluto has not done that. It, in fact, even crosses the orbit, not directly in a way that's going to be disturbed really dramatically by it, but it crosses the orbit of Neptune. And so it has clearly not cleared its orbit of anything of similar size because Neptune is some dramatically larger than this object, and so that is why it is classified differently. So that is the long-winded discussion way of answering that. And so we've got a lot we can go into and answer here. So again, if you have any questions, go ahead and pop that into the chat and we'll talk about it there. Now let's see. I've been talking a bit. You got anything you want to mention?
All right. Before I get to the next question, I'll just throw in a little fun fact that I was taking my very first astronomy course in 2006 when Pluto was reclassified as a dwarf planet. So,
nice.
Do you remember where you were?
I don't remember exactly. I should have been getting really close to heading off to my undergrad in 2006.
Ah, very nice.
Yeah.
Cool. So I'll bring up our next question here, and it is, what is the light year distance from Earth for the 7 major stars of Orion? And we should probably remind people what a light year is, first of all.
Do you want to go into that?
Sure. So a light year is actually a distance, and this question came from one of our employees' husbands. So thank you, Doug. And as I said, a light year is a distance, and it is the distance that light travels in 1 year. So light travels very fast, 3 times 10 to the 8 meters per second, if I remember that correctly. And that is a very long distance, so it's about 5.9 trillion miles or 9 trillion kilometers. We like to use kilometers for our units here. But when they get too far, then we move to light years.
Yeah, so one fun thing with this program is the velocity is indicated way up there whenever I adjust it. The letter C is used to denote the speed of light. Now, as we're flying back towards the center of the solar system, we're currently going at 400 times the speed of light. So that's not physically possible, but it is worth just feeling out how fast light travels through the solar system. So this is 400 times the speed of light we're traveling here. So how long does it take for light to travel, say, from that object bright and shining in the center of the solar system down to the Earth all the way over here? That's about an 8 light minute travel time. It takes about 8 minutes for light to travel that far. So when you're looking at the sun, you are literally looking back in time a bit over 8 minutes. So likewise, if we are looking out well beyond the solar system, how far are we looking? Well, thankfully, with this setup, we can actually turn on our constellations here and look around to try and find Orion. You can always find Orion really easily once you find Scorpius. And let's go ahead and flip ourselves over to the orientation we in the Northern Hemisphere are used to. Well, okay, so the mythological origins of Scorpius and Orion are actually linked. Scorpius, the myth has it, was sent to kill Orion, and in order to save Orion, they were both put in the sky, but on opposite sides of it. So if we rotate around a full 180, we should get pretty close to where Orion is, just below Gemini there. So there's Orion, and there are a full set of stars there. The 7 that were specifically being asked about are the main ones over in the shoulder there, and the shoulder there, and the feet here, and the 3 main ones in the belt. Those are the 7 that are specifically being asked about, and they are all at a variety of different distances. And while we're looking at this, we're going to be working our way into some other questions that have been asked, but let's go ahead and start by looking at that one in the upper left hand, from our perspective, corner of the constellation, Orion's right shoulder, Betelgeuse. Now, Betelgeuse is quite a ways off. There are a lot of different estimates for it, and this will, again, go into actually addressing a number of the other questions that are coming up. So this object has been measured at a number of different distances. If you look above us, it's saying at 427 light years. There are estimates that put it out at 600 light years. This one is a particularly challenging star to get a good distance to. Why? Let's go fly to it and find out. So, Betelgeuse is a red giant star. It is incredibly large in scale, and as such, it can even be directly resolved in our telescope's views. Now, let's go ahead and take a closer look at this. It is, again, so large that it's resolved, and that actually turns out to be a problem because given its distance at on the scales of 400 to 600 light years away, let's turn off those constellations. They're jittering and going crazy. As it is at that distance and we can resolve it, the way we want to actually measure the distance to this object is using a process called parallax. It's what your eyes actually use to give you a depth of field, or rather, not depth of field, depth perception. And the way we use it in astronomy is we look up at the sky from different sides of the Earth's orbit, simulating that same setup of the space between our eyes. And since we can resolve this object, that actually gives us some problems because, again, it makes it harder to pinpoint the exact center of it, and it messes with our images a little bit in trying to do that. And so that's why you get a really wide range for this particular object. Now, as we were flying out here, you probably noticed something, though. One of those stars zipped by us on the way here, and that was because that star happens to be closer. Others further away. So we could go into the specific distances of all three of these, but at that point we're talking about some very specific, just giving you numbers, and we want to give you some of those, but we want to give it to you in context. So where was Earth? Well, let's go ahead and turn our markers back on so we can see what we're talking about. Let's see. Go ahead and hit this button again. Earth's gonna be where all these lines are pointing. There it is. We flew away from the Earth, and all these lines are, again, the lines of the different constellations. And as such, we get to see all of this interesting, weird detail here. Now, let me do something real quick. I want to right-click on this. I want to track that. And now let's go ahead and fly back to Earth. Go. And now you can see the constellation reassemble right there. Okay. And so with that reassembly, we can now look at a few other things. Let's see. Do you want to have any other notes on those things?
No, not for Orion.
Okay.
Thank you.
So let's go ahead and answer one of the other questions. I believe, yeah, let's go with that one. Oh, shoot. Sorry. The one above it. Yeah.
All right.
Because that goes into these stars quite well.
All right, so the next question. Is it true that all stars we see in the sky are already dead?
So the fact that we're looking at Orion is really interesting for addressing that. Yeah. Oh, that's why it's being weird. So do you want to jump in on this one at all? Right
sure.
on? Yeah.
So first of all, this comes from our friend Noble. So thank you for that question.
Yeah, thank you.
And the short answer is no. A lot of the stars are still alive. So if stars last a very long time, they live very long time, millions and billions of years sometimes, depending on their size. So a lot of the stars we see are actually still alive.
Mm-hmm.
Some of the brighter ones, so the brightest, biggest stars, they are the ones that die first. So some of those we may actually already be dead, but there's plenty of stars in the sky still to see.
Yep. Yeah, and that is really, again, worth noting, again, in a very specific context. Which one? Well, we were just looking at a great one. Again, almost everything out there still alive. The one of the few exceptions of that is we don't know about Betelgeuse. It is, again, a red giant star. It is expected to go supernova at some point. It could have exploded anytime in the last 400 to 600 years, again, because depending on how far away it is, and that light may have just not reached us. But 400 to 600 years in a star's lifetime is a blink of an eye. And so, yeah, as Lauren was saying, just about every other star you see out in the universe, still out there. When you start looking out with telescopes a bit further out to millions of years, then some of the bigger, bluer ones might not be there. When you look way out with, say, the Hubble Space Telescope to billions of light year scale, there's going to be a larger fraction that aren't there. But even on those time scales, most of those stars are still there.
Yeah, and we have a question, a follow-up question in the chat from Carrot Cake Man. Thank you very much. And he's asked, since we know stars are still being born, isn't it logical to assume that all stars cannot be dead?
That is
very good point. Thank you.
So since stars are being born, stars do die. And the way we talk about star death is through the processes that end the normal process of nuclear fusion at their core. There's a lot of different normal processes for nuclear fusion. The main one is fusing hydrogen into helium. Our sun will be doing that for on the order of 10 billion years, and we're about 4 billion years through that, 4 to 5 billion years through that, closer to 5 probably. And so, on those time scales, yeah, when you're looking out, it is very reasonable to expect that the stars you're looking at are not dead. They're all, by and large, still out there glowing. And with a few exceptions, we do see some remnants of, that is, the corpses of those dead stars. Let's see. Don't know which one it is. Can one of you look up the first white dwarf discovered? And, oh goodness, I'm blanking on the astronomer's name. What was her name? The one that was, yeah, oh goodness. All sorts of fun things to go into with white dwarves.
Sirius B seems to be the first white dwarf discovered. Of course.
Sirius B. Yeah, and
by the Chandra X-ray telescope.
First white dwarf?
One of these images.
Maybe first one imaged, but...
Yeah. First one discovered in 1862.
Yeah, okay, yeah, that wouldn't be discovered by a space telescope, that's for sure. Yeah. So, yeah, I'm trying to remember the discoverer's name.
Yep.
So let's go and visit Sirius B, because it is a really great one to visit. Oh, yeah, I didn't have to go searching for this, because we're looking at Orion. Where's Sirius? It's in Canis Major right there. So let's go ahead and fly off to that. This is actually a fairly close by star on the order of around 8 to 9 light years away. So let's fly real quick. At this scale, you can actually see that not very much of the sky around us will have changed. There's some clear distortion in Orion there, but as we look around, a lot of the constellations just look a little bit distorted. They're all still mostly intact. That's what going 8 light years does. So let's go ahead and swing back around to our friend Sirius B. And so if we are looking at Sirius B, it's worth finding Sirius A. So where is Sirius A? That actually can't tell if, oh yeah, orbits. Orbits help. Okay, so if that's one of our orbits here, we should have another orbit around, because Sirius is a binary star, and about half of all the stars up in the sky are binary stars. Oh, I'm going the wrong way. That's why I'm not seeing it, because it's like straight overhead. So let's drop back down. Sirius A is the brighter star. Again, we're right next to Sirius B, and that's why it looks less bright. But Sirius B likely was a star somewhat like our own sun, but as it ran out of fuel, it will convert all of that hydrogen in its core to helium, leaving behind something like this. Let's see if we can actually get in here. And what happens over time is that helium can begin to fuse into carbon and oxygen. Yeah, the view here is not adjusting our exposure. Let's try doing this button. No, that doesn't look real. That's not right. But so you end up with a lot of carbon and oxygen in the core of a star like our own sun, and that process of fusing helium into carbon and oxygen, it can cause a star to puff up really dramatically. Again, you end up with a red giant, not like Betelgeuse. Betelgeuse is a much more massive star, but you can end up with a star large enough to consume many planets around it. For example, when our own sun turns to a red giant, it will likely consume potentially everything out to the orbit of Mars, working its way out even close to Jupiter. But that is a relatively small red giant, and this one likely went through a similar process. But after that, the outer atmosphere of those stars can puff out and leave behind the seething hot mass that was the core of that star. And that is why they end up so nice and really bright and blue. They lean on the blue end of the spectrum because that is the hotter end of the spectrum with our black body radiation. And eventually this will cool down, but that's going to take a very, very long time. Yeah.
So in the meantime, as we're looking at these bright stars out in the sky, we have another question from our friend Jeffrey about why do stars twinkle?
Ah, that's a good question. So we'll fly out here just so you guys get to see that orbit. Yeah, always fun to see binary stars' orbits. Excellent
Definitely.
question. So why do stars twinkle? Well, to answer that, it's worthwhile to try looking at things a bit differently. This program here is Stellarium. If you've seen some of our live streams before, you've probably seen this. This is a simulated sky program, and this particular view is right now here from the observatory. Looks a little bit different outside, but again, everything's simulated. So what we can do here is we can actually adjust time and even turn off the atmosphere. Now, one thing that's fun to note in this view is what happens right at the horizon. When let's actually go ahead and get the sun below that horizon. There we go. Now with the sun, well, let's get a little lower. We don't want any sunset scenarios. All right, with that all down, it is worth actually looking at the atmosphere turned back on, and let's turn on some orbits here. Now, what's noticeable here is there's a weird bend going on right near the horizon in this program, and that is because this program actually works in what the atmosphere is doing to light as it enters. Right near the horizon, you actually get a bit of a bend in that light. It's really, really slight, but you see some things shift from where they actually are. And again, if you don't see that directly, toggle the atmosphere back on and off, and you can see how some things are moving. In fact, this evening, looking at Antares, you can actually see it moving. Oh, hey, we got a satellite.
Nice.
Anyway, yeah. So that distortion happens, and we even have shown here a bit of twinkling with Antares as well. It's very subtle, but it's there. And that twinkling is, as we astronomers like to give it a fancy word, is referred to as scintillation. And it is literally as light comes into the atmosphere is not a perfectly still unified thing that only interacts with light in one way. It actually can bend it in a bunch of different ways and cause our view of a distant point source of light to move about a bit. And that is referred to, again, as scintillation. It's measured in a property called seeing, which we can go into. I lost my button. Where'd it go? Uh-oh, did I delete this button? Oh, well, I thought I had a button for it. Here we go. This is a wonderful site called cleardarksky.com. Highly recommend checking it out for stuff near you. This shows all sorts of things about sky conditions. It's part weather, but largely focused on astronomical observations. And you can see in there a nice row called seeing. And that row tells you just how twinkly those stars are going to be. Let's see. So what do I mean by that? Well, if you are looking over here at seeing, you can actually, in this program, or in this website, rather, you can actually go and mouse over the individual things, and it's not capturing in the software, of course, but that color blue is average, 3 out of 5. The darker it is, the better it is. The lighter it is, the worse it is, because of course it is. This is astronomy. You want nice and dark things. And so you can even see in this setup where the moon is by looking at that section there. Yeah, so it's great to be able to get a forecast on what you actually can expect the twinkling level of stars to be. If you have particularly terrible seeing, you can actually see some planets start to twinkle a bit. They don't twinkle as much because they are more than point sources, so it takes a lot more disruption of the atmosphere to actually cause them to shimmer in the night sky. But yeah, that is an excellent question, and thank you, Jeff, for that one.
Yeah, thank you.
Yeah.
So in the news lately, we've seen several civilians go up into space. So this question kind of leads into that. Where does space begin?
That's a good question. Let's see. Let's go ahead and jump back to SpaceEngine for that, because it'd be fun to go there. All right, which means we need to get back over to the Earth. Not the Eagle Nebula, but if someone has a question on the Eagle Nebula, I'd be happy to go there. All right, so back to the Earth. Whee!
And this question comes from our friend JD.
Yeah.
Thank you.
So the atmosphere of the Earth is surprisingly thin when you actually go and think about it. Let's see. Are we in our present time frame? There we go. Okay, let's go find us, because we're used to looking at our own place over here. Whee! Okay. Let's see. Don't know if it's looking choppy to people actually watching or not. It looks like it might be. Okay, so this right near Earth, it might actually be a little choppy in the program. That's good to know. Okay, I'll go slower. So the atmosphere of the Earth is, again, surprisingly thin. And as it is made up of air and not capped with any sort of physical hard object, it might make sense to you that the atmosphere changes over a long distance. And by long distance, I mean astronomically short. But in any case, the way we actually start talking about space, there's a few different definitions. One of the most well recognized is what's called the Kármán line, or von Karman line. It is 100 kilometers up from sea level. And so as we are right here near sea level, 100 kilometers up, or around 62 miles up, is not all that far away. The area we're looking at the Earth right now is much larger than that. In fact, if someone wants to measure the length of the Salton Sea, that would be a good comparison.
Sure.
But yeah, so the so that distance of 62 miles, or 100 kilometers, where does it come from? Well, again, it was first postulated by a number of people, mostly though Mr. von Karman, and in actually trying to figure out what would be a good defining line between space and atmosphere. It's a funny thing. It's really much more a Earth-based viewpoint to actually talk about where does space begin. It's really more where does Earth begin from the outside, if you're looking at it that way. But in any case, when we're looking at the Earth and trying to actually figure out that atmosphere, the things that will help will be talking about the dynamics of it all. Let's go ahead and slow down a bit. And whoop, that was not slow enough.
And just for reference, the Salton Sea is about 35 miles long.
Yeah, so where we were looking there, about twice that distance. Okay, so as we're flying up through the atmosphere here, that's not the Salton Sea up close, that's the Salton Sea further out, I believe. Yeah, because we ended up in Mexico because I crashed. Told you I'd crash. But yeah, so again, that defining line going for the Salton Sea as shown here, about twice that vertically. gives you a rather thin envelope over the Earth, which is again on the order of around 6,000 miles in radius. No, 6,000 miles in diameter. It's 10,000. Yeah, kilometers. Yeah. Okay. Gotta remember, it happens all the time in anything with astronomy or sciences in general and engineering especially. That factor of 2 between radius and diameter always comes and gets you. But in any case, that thin envelope of air around the Earth, if you want to find a limit of it, what is a good way to actually look at that is where can you actually put things into orbit around the Earth? When you try and put something in orbit, if you have something that has its closest approach to Earth near that 100-kilometer mark, it will potentially stay in orbit a little bit, but it will experience quite a bit of drag at that lower part. If you try to put something with a closest approach to Earth below that 100-kilometer limit, though, then it's probably not going to complete its orbit anywhere remotely close to what it was. And so that is a good way to actually start talking about the atmosphere and how it actually interacts with objects. Another thing that's important to look at is where meteors actually burn up in the atmosphere. A good chunk of them burn up between 70 kilometers and 100 kilometers up. And that is a good way of actually saying, oh, well, if something is entering the atmosphere and burning up in the atmosphere, you should probably define your limit of space above that. You'd think. But there are other definitions for the edge of space, and the Kármán line is the one recognized by the FAI. It is the international group that sets a lot of standards, and it's really important to have that. Again, this is a very Earth-centered view of things, because why is this important? Well, it's very important for a lot of political reasons, in particular international politics. If you want to have something flying over another country, well, if you have that defined vertical space for that country that is in the atmosphere over the country, that's kind of important. But it's also something that goes into where you define when someone's gone up into space, how someone gets their wings, as it were, their astronaut wings. And it's that particular note that makes the US a little bit different, because the US military has a little bit lower definition. Let's see, that one I want to say was 50 miles instead of 62. And that results in a little bit of a different way of doing things. And for NASA, they shifted to the military definition. I want to say it was actually pretty recently, back in like 2005-ish. And that was because, well, if you have Air Force people and civilians on the same craft and they go to 55 miles up, it's kind of weird to give only some of the people on board those astronaut wings. And so that was one of those things that led to that particular decision. But so where does space begin? It's an interesting question, and it's one that there's a few different ways of looking at it. My favorite way of looking at it is more, where does Earth begin? And really, yeah, it's basically just a little ways up above the surface. By a little ways up, yeah, okay, we can just say von Kármán line works. I'm good with that.
Works for me.
Yep. Anyway, I've done a bit of rambling on that.
So another somewhat ambiguous question from our friend Jerry is, why is there no gravity in space?
That is an excellent question. So let's go ahead and answer that by visiting a cool place, the International Space Station. I have no idea where it is right now. We might crash into the Earth trying to get to it. Let's find out. Oh, we're going to crash into the Earth. Sorry. Make it stop. There, it stopped. Okay, it's safe to go back now. Whee!
Almost there.
Almost there. Up we go. All right. So the International Space Station is a great thing to take a look at here. The International Space Station, as this model has it, is a little bit slightly dated, but in any case, this view of the International Space Station highlights something really important. That red line going through it is the orbit of the International Space Station. And you've probably seen some footage of astronauts on the space station floating about weightless. And that is likely why you end up with this question of why is there no gravity in space? Well, in fact, there is a lot of gravity in space. The weird part is really, again, in how you think about it. When we're looking at this object here, if you are on that object, you're moving with it, and it is in orbit, which means you are also in orbit. But what is in orbit? Well, let's go ahead and actually, hopefully, we don't end up with too much of a lost frame rate here. Let's see. Now I want to show this orbit, and I want to fly away from it. I want to see this orbit all the way around the Earth here. Whee! Oh, there's a little bit of that lag. All right, that's probably good enough. Shift this down around there. There's a good view right about there. Okay, so from this particular setup here, we can see the whole orbit of the International Space Station. Now, while we're looking at the International Space Station, what we can also consider is that if we have the International Space Station and it sits stationary there, there is gravity up there, and what would happen is it would fall straight into the Earth. It would fall into it very quickly, and that would be a problem. But thankfully, it's in orbit, and if we go ahead and hopefully this works, actually, I want to lock onto this. Let's follow this object, and let's hope that the, oh, nope, it did not do what I wanted it to, because now we lost the orbit of the International Space Station, which is kind of important for this discussion. Okay, so as time progresses, this object is moving so fast horizontally, that is parallel to the surface of the Earth, that by the time it would fall enough to hit the Earth, it has moved around it. And so again, by the time from this point it would hit the ground here, it has gone so far horizontally that it has missed the Earth. And so how do you get weightlessness? Well, you get weightlessness by free falling. And that is why there seems to be no gravity in space. It is actually a bit of an illusion of simultaneous free fall. We can actually even simulate this. If you were to put a camera into a jar with a bunch of little dice or Legos or something else, and you launched it up into the air, there'd be a little bit of drag from the air that would slow it down a bit. But for a good chunk of that flight, when you throw it up in the air, it would look like everything was weightless because everything will be moving together. This is how you end up with or vehicles like the famed Vomit Comet, the aircraft that flies in a parabolic arc to simulate weightlessness for people on board. It's not actually simulating weightlessness. It is demonstrating weightlessness, because microgravity, what you experience on the space station, is the same. It's just the scale of your projectile motion is much, much larger, such that you circumnavigate the planet. In the case of the International Space Station, roughly every 90 minutes. And so it's free fall that makes that expectation, that feeling as though there's no gravity in space.
Yeah. And along those lines, they use planes following that parabolic arc in a lot of filming of shows. So in Apollo 13, that's why the astronauts actually look like they're floating around, because they are.
Yep. Yeah. Fun fact about the setup for that: if you are flying in parabolic arcs, you get roughly around 30 seconds of weightlessness. So there aren't very many long sweeping shots in the interior of the spacecraft in Apollo 13, because yeah, they had to actually film those in the time frame they actually experienced weightlessness. So very impressive how they filmed that particular movie.
Yes. All right. So let's zoom out a little bit and go to our question from our friend BT. And he asks, is the universe collapsing or expanding?
Ooh, excellent question. So to actually begin to address that, let's go ahead and stop this. And I actually want to go back to, well, hang on. Do this, get me up. Back to normal time scale, get me back to the present. And let's go ahead and leave the Earth behind here to actually start talking about things on a much grander scale. So the question itself, is the universe collapsing or expanding, comes to a specific scales in which we understand things, and that is on the extragalactic scale. In the, let's see, it was just about, or on the scale of 100 years ago, when we first figured out that the Milky Way was but one of many galaxies. All of these lights around us right now are galaxies, big giant island universes, if you will, with hundreds of billions of stars in just about all of them. There are so many of them. But Edwin Hubble first verified that the Andromeda Galaxy was in fact a completely separate galaxy, and it'll be one of the big ones hanging out right near the Milky Way here. I want to say it was down. Whoa, goodness. Sorry. Let's slow that down. Yeah, going a few million light years a second makes for some dramatic motion. Okay, so let's see. The Milky Way is right in front of us. Where did Andromeda go? Anyway, he found it, and though his estimate wasn't exactly the greatest, oh, actually, I'm way far away. That's why. It's that one right there, that bright one. Is it? No, that doesn't seem like the right scale. Anyway, again, his first estimate wasn't the greatest, but that we have now, but it was the greatest at the time, and it unequivocally verified that the galaxy was well beyond the outskirts of the Milky Way. At which point, we had seen objects that are very similar in appearance to the Andromeda Galaxy, and so Edwin Hubble went and started looking for a number of them, went to find the distances to all of them using the method that Henrietta Leavitt developed, that of Cepheid variables, and he was able to calculate the distances to the objects, and using some other methods, we figured out the velocities in which these things were moving. He found a correlation between the distance to the object and how fast it was moving. In particular, how fast away from us it was moving. By and large, as we look further out, things are moving away from us faster and faster. There are a few exceptions to that, but they're all really quite close by, and that's due to the fact that galaxies are moving with respect to each other. That said, when we are looking out at the whole universe, what we see is that everything is moving away from everything else. The universe is in fact expanding, and it will be, as far as we know, for a very long time, which leads us to, I think, another question.
Sure. So our next question from Buddy is, what keeps space empty? Which somewhat relates to the question you were just answering.
Yep.
And from this view, you can see that space isn't totally empty.
Yeah.
There's a lot out there.
Let's see. I don't want to let myself not find Andromeda. I have to look at it. It was up there the whole time. It's up here.
So it's
there
last
it is.
place you look.
Yep. The thing about space is, yeah, there's a lot of space in space, but that space is filled with quite a lot of things. They just happen to be spaced out very far apart. The Andromeda Galaxy is a great place to visit to actually discuss this, because there are on the order of around 1 trillion stars here. This is the nearest large galaxy to the Milky Way, and again, there are so many stars here that you might think it's pretty densely packed. I mean, we can fly right through here and see all sorts of lots of stars everywhere, but there is a lot of space in between these stars. And so what keeps it empty? Well, to some extent, it's the fact that it's not entirely empty. There is actually material out there. In between stars, we call it the interstellar medium. In between galaxies, it's the intergalactic medium. And there is stuff there. It's just spread out very far. And when we are actually looking at things on the scale of looking at the Andromeda Galaxy and the Milky Way, which was down here, right? I didn't lose our home. Oh, we're lost in space. Anyway, those two galaxies, the Andromeda Galaxy and the Milky Way, are actually on their way towards each other. And in roughly 4 billion years, they will collide. But there's actually so much space in between the big objects that we don't expect stars to collide in that process. We expect the galaxies to actually pass through each other smoothly. They'll distort each other with their own gravity, and they will mix together to eventually form a very large galaxy. And it's worth noting, though, that in that process, something happens, and it has to do with the fact that space isn't entirely empty. And to address that, let's go ahead and find our way to M87. It wants a space. There it is. Okay. M87 is one of the largest galaxies in the Virgo cluster of galaxies. It's way down here. There went the Milky Way. I knew it was down there. All right. The Virgo cluster of galaxies has a few hundred galaxies in it, if I'm remembering correctly. Or is it on the order of thousands? It's hundreds. Yeah. Groups have on the order of tens. All right. So as we fly up to this galaxy, it might be sort of surprising. You may be used to seeing big spiral arms around galaxies and such, but this is what happens when you actually have galaxies like the Milky Way and the Andromeda Galaxy collide. You'll notice the color is very specific here. It's rather orangish, yellowish. There aren't too many blue stars here to give it that blue spiral arm structure that you're used to seeing. And that is because in the process of two galaxies colliding, the gases there, the interstellar medium collides as well. And that drives the formation of a lot of stars. And that is, again, one of the things that actually keeps space as empty as it is. When you actually have those gas clouds colliding and actually forming stars, a lot of that material is collected into those individual, rather small points relative to everything else. And as a result, you end up with relatively empty space. There's still some material that escapes that doesn't get collected into those stars. That, again, would be that interstellar medium. But when you have two galaxies collide, a lot of that stuff gets smashed together. You get a lot of stars formed all at once, and then there isn't much material left to make new stars. And when you're looking at stars that are fusing hydrogen into helium, if you see a blue star doing that, that is going to be a more massive, younger star, or rather a star that has a shorter lifespan. If you see a lot of stars that, again, are fusing hydrogen into helium only in their core, they appear red, they're going to be lower mass, and they last a lot longer. And as such, a place like M87, like this, ends up looking pretty quickly, on astronomical scales, in a rather reddish orange, or in this case, yellowish hue, because there's a lot fewer of the blue stars there. You can see some here, and some of these will be simulated. But yes, that color is driven by the fact that the more massive stars all already died off, and there isn't material to make new ones here. It's already collected, keeping the space there empty.
One of my favorite fun facts about colliding galaxies is that the ratio of the size of the galaxy compared to how far away the next galaxy is much smaller than the one for how big the star is compared to the next star neighbor. So it seems like it would be easy to smash stars together, but it's actually a much smaller target to hit one star against another, or have to have them collide, compared to one galaxy colliding with another galaxy.
Yep. Always a fun place to go when talking about colliding galaxies.
Definitely.
Is the antenna galaxies. Now, these objects are colliding, and while we don't have as good of simulation while the simulation might be taking a few liberties, it does give you an idea of what's happening here. We see what look like two tadpoles attacking each other. Well, in fact, they are two galaxies, and as drawn here, they're actually drawn as spiral galaxies that have been very distorted. They've passed through each other once, and while it may not be apparent on the live stream, it's hard to say, you might be able to see this big arcing path right here of stars just moving out in this whole direction here. And that will come from the fact that the gravitational interactions of these two objects have cast out a bunch of stars. And that is what drives the name, the antenna galaxy. Because you can see, if you're looking carefully, you might be able to see those two antennae going on either side of the nuclei of these galaxies. Again, if we highlight them again, you might be able to spot them. There's one right here and one over this way. All of those stars out in those reaches used to be towards much closer to the centers of those galaxies, but the interactions just threw them out. It did not destroy them in collisions. But yeah. All right, that was an excellent question. We went all over the place with that one.
Awesome. Yeah, thank you.
Let's see.
So the next question, as we wrap up, I thought might be kind of fun, is what is Eric's favorite planet and why? And before Eric answers, I'll just interject that my favorite planet is Earth. Taking the easy way out, I know. She's
trying to take, really, when you're talking about planets and actually where you like to be, it's hard to beat Earth. I mean, she answered that one because, quite frankly, that is basically the correct answer. You like Earth. You might have a favorite planet the way someone has a favorite dinosaur, but when you think about actually interacting with dinosaurs, you might have a different opinion of that once you actually meet them. When we're talking about what we actually like in a planet as living human beings, yeah, Earth kind of wins. So I'm going to stretch beyond the planet definition, and I'm going to actually go talking about one of my favorite places in the universe. And when I talk about a place, keep in mind, I'm an astronomer. I like good views. That shouldn't surprise you. We look up at the sky because we love looking at things out there and exploring the universe. And so where might we find a really good view? Well, my favorite place, as far as good views go, is at the moon Mimas. If I can spell it right. There it is. Mimas. It is a moon of Saturn. And so, well, I was flying the wrong direction. That way is back towards Earth. So let's go. All right. So as this flies off over there, yes, I really love this little moon. It is a wonderful moon that interacts with Saturn's rings in a really interesting way, but it has a very specific, spectacular area on this moon that has a phenomenal view. And I want to turn off all of these little markings because I want to see really nicely. All right, so Mimas is a great little place. Yeah, it is not a place that's very hospitable, but I mean, yeah, you live out here in the desert, you aren't necessarily looking for the most hospitable place in the world. But nevertheless, this place has a lot of great things going for it. All right, so that way would be more south. And there's Saturn's rings. There's Saturn right there. And so I'm going to go ahead and move our time around because I want to see some things here. Let's fly on off around to the other side of Saturn. Now, oops, wrong way. One of the fun things about Mimas is its nickname. Let's go ahead and pause that there. It is known as the, by its nickname, the Death Star moon. And that is because of that big giant crater there. That is Herschel crater. So if I position things just about right, like right around there, yeah, you start to see that, that comparison with the Death Star there. But finding Herschel crater is important because the place I'm looking for is right near the rim of that crater. Let's go ahead and fly our way on down there. Spin off this way. I want to be this way more. Let's see. It's right on this northeast end of the crater. Right on down here. Yeah, right over here. Oop, I'm running into a little bit of lag. I'm going too fast is what's happening. Let's slow down a bit. There we are. And as we come down right about here, let's just plop ourselves down. Plop. There we go. Now, if you are on Mimas, this is the view you get. And the beautiful thing about Mimas is, like our own moon, it is tidally locked to Saturn. Well, like our own moon, it is tidally locked. This one to Saturn. Yes. Our moon to Earth, of course. But what that means is as we let time advance, Saturn doesn't go very far in the sky from there. it hangs out right there, and it is covering a rather large section of the horizon there, on the order of around like 20 degrees on the horizon. In comparison, the sun is around half a degree wide in our sky. So if you watch a sunset and it looks pretty and it's just sitting there, yeah, that's great. This is covering 40 times that on the horizon. And the rings will stretch something like 60 degrees up from that horizon at this particular point. I love the view here. It is really, really great. And actually, in this program, we can change our field of view and see a bit more. And as you're looking at it, it's not just a static view. Because you're orbiting around Saturn, you get to watch it change over the course of around 24 hours, because the orbit of Mimas is very close to the same time as it takes for the Earth to rotate once on its axis. So you get this really dramatic set of events over the course of 24 hours. I love this spot. I would love to just sit there and enjoy the view for a very, very long time. That's my favorite spot. Do you have a favorite spot?
On Mimas?
Just out there.
Spot. Let's see.
That's why I was expanding the definition beyond just favorite planet.
Yeah,
Earth
that's a
is such
point.
an easy
Right.
way to get out of that.
Yeah, my favorite view would probably be from maybe Mars, so you could look back and see the Earth a little bit in the sky.
Mars is a really cool place. It has a lot of great views there. Let's swing on back over and try imagining that real quick. Let's see where we're at. We aren't close to opposition, which means we aren't that close to Mars in our orbit.
Yep, I noticed earlier in Stellarium it was very close to the sun today.
Yes, which means we're looking. All right. Oh, we still have time progressing. Let's stop that and let's go ahead and get back to the present. Though if I hadn't, we might have had some different things going on. All right. Anyway, let's go ahead and plop ourselves down. Actually, I want to say this is up. There's a. Oh, we're on forgetting the name of this mountain. If you want to hear me say the name of this mountain without me having to remember it, I do in the Distancing with the Stars video we did. This particular mountain, it's like Elysium Mons, I believe. Yeah, might be.
Very nice.
Yeah, it's a nice big old mountain. And we'll just plop ourselves down on top of it. There we go.
Beautiful.
And from this place, let's go ahead and turn on our orbits. And where's the Earth at? There it is. All right. So with this setup, yeah, this would be a very bad idea to do this right now if you were on Mars right now. But let's go ahead and work like we've got a telescope and actually look back over towards the Earth here. There we go. Okay, it's moving. Let's pause time so that way we don't have to deal with it moving. There we go.
Beautiful.
So since we are quite close to that time frame where when we're on the opposite side of the sun, we get a very full Earth right now. And you can see that distance between the Earth and the moon, except that looking at the live stream, there's the moon right over that way, right there.
Yep.
Straight over there. And so this is a great place to end it off because, yeah, one day we might be able to actually get such impressive views looking back at that big old blue marble. Of course, we've had some things. We've had the famous pale blue dot image, but we haven't looked at the Earth from such great distances with our own eyes. And so hopefully one day before too long, we'll get a chance to do that. But yeah,
That's a dream.
I think you've got a great view choice for your favorite there. But yeah.
Excellent. Thank you.
Anyway, with that, I think we are going to go ahead and wrap things up.
Yep.
And so thank you all for joining us. Thank you, Lauren, and thank you, Ron.
Thank you, Ron. Thank you, Eric.
Appreciate everyone who's been here and everyone who gave us some questions to go through. We hope you all have a wonderful day. And of course, a special thank you to the Rancho Mirage Library and Observatory Foundation, who makes programs like these possible. And with that, again, thank you all for being here. And remember to keep on looking up. Good night, everyone.